pocket. No, there was this ritual did it's like happy birthday party. And my mom's and my grandma's.
Let's go ahead and get started. We'll try and finish up the stuff we need for statics today. I understand there might be some questions on the homework. If they involve center of gravity, we'll cover it today. But if not, we'll I'll answer.
1.7, I don't know if that.
Okay, so 4.7 says a uniform lever arm is used in conjunction with a pivot to weigh an object A. The mass of the lever arm is not negligible, but is unknown. The pivot point may be moved relative to the lever arm. All right, so if we can get our heads around it and maybe draw a little picture, a lever arm, treat it like this, and then a pivot point can be moved. So there's my pivot point, and this thing can be moved back and forth. Okay. Where should the pivot be placed along the lever arm so the mass of the lever arm does not appear in the calculation? Well, we got to move it on. Then here's maybe an object A that's hung from there. Well, the lever arm will have some sort of center where gravity acts. So you would want to place, it does involve center of gravity, you'd want to place probably the pivot right at the center of this arm. And that way if the gravity force on the lever arm acts there, so this would be the force of gravity or weight of the arm, then this won't exert any torque because it's right at because that R perpendicular to the pivot point is 0. Make sense? Okay, and then B. If an unknown mass is balanced by a 0.5 kilogram mass hung on the lever arm 1.15 meters from the pivot point, how much does the unknown mass in a given that it's hung from the lever arm at 0.3 meters the other type of pivot point? All right, so this is 0.3 meters. And then we have a mass 0.05 kilograms at 0.15 meters. That thing's balanced. And so what would we do here? Yeah, that's right. So I balance the torques here. So sum of torques is equal to 0. This torque the torque due to this mass makes it want to rotate clockwise, right? Then B minus the torque due to A plus, well, okay, let me just write these down. So torque due to A would be the 0.3 meters times mass A times G. And then there's a minus sign because it makes it want to rotate clockwise. And then the torque due to object B, just going to label this as B, is going to be 0.15 meters times 0.05 kilograms times G. If I sum up the torques, that has to be 0. For statics, and then get exactly what Alan said, you'll see that we get minus 0.3 meters A G plus 0.15 meters, 0.05 kilograms v is equal to 0. Or bringing this over to this side, 0.15 meters times 0.05 kilograms times G is equal to 0.3 meters. Mass of A times G. The G's cancel. If I divide everything by 0.15 meters, this is 2, right? 0.3 meters divided by 0.15 meters, that's simply 2. So you get 0.05 kilograms is equal to 2 mass of A. And so the mass of A is, dividing both sides by 2 is 0.025 kilograms. And you could have done that really quickly, like what you said after, I mean, clearly the torques are going to balance. I just wanted to go through what the process would be, which is what you'd go through for more complicated problems. Okay? Does that make sense? All right. Well, I want to talk about center of gravity today. By the way, is there any other questions on the homework? Okay. I want to talk about center of gravity today. Center of gravity. And so the idea of center of gravity is this would be the point in a complicated object where you can treat gravity as acting. So say I have a complicated object like this. If I had a center of gravity here, and I'm going to write this as C. For the sake of rotations and movements of this object, I can treat all the gravity forces acting at that point. So for instance, if I threw this in the air, this thing might be spinning around the center of gravity, but the center of gravity would be what would form a nice parabola as it went up in the air. And you could treat this as a point that just moves and accelerates with the acceleration g. So that's the idea of center of gravity, is that we can treat that as the point at which gravity acts. We can figure out what the center of gravity is for complicated objects using a fairly simple experimental technique. I'll show you that in 1 second. Let me just kind of preface this. Let's say I have a rectangle. Treat it like this, okay? Like this thing. Okay? Or maybe a sheet of metal or something like that. And let's say the center of gravity was right here. Let's say that I suspended this from this point right here. So let's say I held it here. Well, the gravity force, the weight, would act over here at the center of gravity. You can treat it like that. R perpendicular from the suspension point is like this. So there's a torque here, right? And this thing would want to rotate downwards. Well, would want to rotate clockwise if I was holding it at this point. If I were to suspend it, not at that point, but one just a little bit over, so maybe over here, then R perpendicular would be like that, and this would want to rotate counterclockwise about that point, right? Now, if I suspended it right above the center of gravity, like right there, our perpendicular would be 0, wouldn't it? And it wouldn't want to rotate. So this so if we suspend an object so that its center of gravity is directly below this or above the suspension point, it doesn't want to rotate. And this gives us a way to figure out where the center of gravity is. Let me illustrate, and I'm going to need a little drawing. So for instance, I have a little suspension point here, a pencil. Hopefully it rotates pretty well on this. Okay, so if I hold this up, move it down like that, I know that the center of gravity will be somewhere below the suspension point once it's reached this nice stable equilibrium. There's a torque here, and it'll rotate, and it'll eventually find some sort of place where there's no torque. And if I were to just draw a line, I don't know if you guys can see this. If I were to draw a line straight below the suspension point, I'd probably want to get maybe a marker. I'll try it with a marker. So holding it upwards so it's free to move. If I were to draw a line straight down from here, center of gravity should be somewhere on that line. It's not a very good line, is it? All right. Somebody, I need a helper. Anyone willing to volunteer? Can you draw a line straight down from there as best you can? It'd be ideal to have like a little plumb bob or something to draw it along. I probably should have thought of that. That's much better. That's good. Okay, now somewhere along that line is the center of gravity. Wait. Okay. We're gonna need one more.
You've got the intersector line.
Somewhere along this line is the center of gravity. If I go to a different suspension point like this, let it rotate. Somewhere on a line directly below here will also be the center of gravity. See that? And where these two things meet,
Did I follow the pencil? I don't know.
yeah, I don't know. I think it's kind of more down like that if I look at it. Yeah.
Theoretically, it ought to hit the middle.
Yeah. So, where these two lines intersect, that should be the actual center of gravity. Okay? And because below any of those suspension points where it's free to rotate, that's where it'll be. So if I take two places to rotate, I can supposedly figure this out. That doesn't quite look like this. Anyway, it helps if you have a plumb bob. Let's just put it that way. But does that make sense? Now we could test to see if this was true or not. I could put a hole through here. See if it wants to rotate. And if I rotated it like this, I should feel it fairly stable. And it doesn't quite feel that way.
That's because it's
Fly wheels along.
Yeah. So, anyway, there's probably...
So for that, couldn't you just take a line from the corner to the from like the upper left to the bottom right corner, and then just find the center there?
Well, that's ideal if you have a uniform density object. If this were, not quite uniform, so that it got thicker, maybe on this side than this side, or had various masses somewhere in here, this method should work regardless. Should work. And if we were careful, it would. But yes, as you're saying, if you assume a nice uniform object, yes, you would have found it that way. In this case, well, it should be much more closer to the center than it is. What's that? Yeah, maybe that's it. We took out enough of the mass by drilling holes in it, but the center of gravity actually is there. Somehow I don't think so. All right. But the idea of center of gravity is important. Yeah, this is just a method to find it. In practice, it's quite useful for figuring out stability of objects on like inclined planes. So for instance, let's say I have an inclined plane like this, and I wanted to, and let's say that this angle is theta, and let's say that I had a box and I was trying to push up this inclined plane, and let's say that the center of gravity is halfway up that box. Let me make it a little clear. Let's say it's down here first. Okay. If this plane is too steep, even if the box doesn't slide, it can tip over backwards, right? When it tips over, the box is effectively rotating about this point. Tipping box rotates about that back corner. So if I have a box like this with a center of gravity here, the weight force goes down like this, right? The distance between the rotation point and the center of gravity is like this, right? This is R, perpendicular. And do you see how this makes it want to rotate clockwise, makes it want to stay on the plane? You see that? So if this is
shouldn't it be rotating
counterclockwise?
or clockwise, right? It makes it want to stay on the plane.
I thought it was rotating that way and falling backwards.
Well, if I have as long as I have the weight straight down here and R perpendicular like this, the perpendicular distance from the rotation point to where the force is,
Okay.
this one would make it want to rotate this
Down.
way.
Yeah,
that
yeah,
one makes sense.
Yes.
Outwards. Yeah.
So this makes it so this the torque about this corner makes it want to stay on the plane. Now let's suppose that I stacked the box so that its center of gravity was not there, it was not low. Well, let's say I had it upside down or something, so the center of gravity was up here. And then this is my corner. Well, if the center of gravity is up there, the weight force goes down here, like this, right? In that case, the R perpendicular, the distance from the suspension point to the weight, or from the rotation point to the weight force is right like this. So the torque due to the weight now makes it want to rotate counterclockwise, right? So that means that this box will fall over. It'll rotate on this back corner and just fall right over. Does that make sense? So as long as the center of gravity is above a point on the box, you'll get a rotation that makes it, you get a torque that makes it want to not fall over. As long as the center of gravity is above a place that's not on the box, it'll want to fall over. And so this allows you to figure out things like maximum angle a car can go up, or maximum angle you can build you can put a box at or something without it falling over. And so we can go through some more examples of that. We'll do this inclined plane one. I'm going to call this angle theta. And then I'm going to have a tall object with center of gravity at a height on the object h. And we'll call the distance from this corner to halfway up that, to where the center of gravity is L. Okay? I guess I could call this h over 2 or L over 2 for half the width of the total width of the object and half the total height. That's assuming that this center of gravity is at half the total height and half the width. Okay. Well, the weight force acts on that object, right? Acts on the center of gravity. This angle here between the weight force and the line that goes perpendicular to this plane, this angle is theta. That's the same, you can get that from the same reasoning we used, that would be the angle theta for a block on an inclined plane. You can see that if I adjust this theta down to 0, that this angle here would adjust down to 0. Okay. And if I adjusted this angle up to 90 degrees, this angle here would adjust up to 90 degrees. So they'll be the same angle. So, as long as this weight force, as long as there's some r perpendicular, as long as the center of gravity here is over the box, this thing won't want to fall over. We'll want to rotate over. That means that this distance, let me draw this. That means that if I broke up the weight force into components like this, that distance there, that component there, well, that means that if I take the h over 2, let me do this. Tangent of theta, that would be the L component of the weight, the y component. Well, let me draw this. X, y. That'd be the x component of the weight force over the y component of the weight force. I mean, it doesn't really matter. But as long as tangent of theta is less than h over 2, L over 2 over h over 2, or as long as tangent of theta is less than L over h, you'll see that the weight force acts so that it would be, so that the center of mass would be right over the object still. This is the condition for the object to be happily on this plane without falling over. Okay? Condition for being happily on the plane. All right. So I'm going to go give you guys a problem and see if you can figure this out. Okay, let's say I have a dune buggy. Well, we can treat it as a box. You can treat it as rotating around one of these wheels. And let's say that the center of gravity is 0.8 meters above the ground. And that this dune buggy is 2 meters long, and that this center would be 1 meter. The center of gravity is 1 meter over there, or 1 meter over here. So we're assuming that it has 50-50 weight distribution. What would be the maximum angle this dune buggy could go up before it fell over? What is max theta before the dune buggy falls over? So see if you can get that, and then I'm going to go get some whiteboards and give you guys a little group work, okay? And I'll race you on that one. Get an answer? All right, what was the answer?
51 degrees.
51.3 degrees. Good. So that's the maximum angle it can be going up or down without falling over. So we got that because the L over 2, the distance between the center and where the center of gravity and where the rotation point is, which is this back wheel, 1 meter. H over 2 is 0.8 meters. And so tangent of theta has to be less than 1 meter over 0.8 meters. So the maximum possible angle that you can have, because tangent of theta just increases as angle increases up through 90 degrees. So this means that theta max will be equal to arc tangent of 1 over 0.8, which was 51.3 degrees. Good? And so that's a pretty big angle. By the way, the Hummer H1, they say that they can climb up to 60 degrees or go down up to 60 degrees without falling over. Of course, you have issues at those angles with the ability of the wheels to actually have any grip on there, but you know, this is apart from that.
What's the angle it can go up to?
60 degrees for the Hummer. So that means it has low center of mass, very long body. There's a type of car, the Mercedes G-Series 6x6, and that one actually has a second wheel back here. You can see why you would want to add such a wheel, because if they didn't really move the center of mass over, they just put another wheel backwards. And so it really lengthens it that way. And it gets much higher angle of climbing with that extra wheel back there.
What about when you go from a wheeled vehicle to a tracked vehicle?
Well, the tracked vehicle, for this thing, it doesn't really matter. Let's have a track here. The track would, of course, have lower ground pressure, be able to get more grip. But the fact of the matter is that back here, if the center of gravity were still back over here, you know, we're not above the object, it would still want to fall over. So if I put the center of gravity here, it would still want to make it rotate backwards.
So when they add the extra wheel, for your value, would you use the L over 2, or would it just be the distance from the, yeah.
Yeah, it would be the distance from, so if I had the extra wheel, let me just do this.
Yeah.
And then I have an extra wheel back here.
Uh-huh.
Center of gravity here, and if I called this L over 2, and this thing maybe something else, it's distant from the center of gravity to the suspension point. That's
Okay.
what I would use, okay?
All right.
So, and then here if I called this H,
Still the H.
H over 2, I would use the tangent of the angle to be less than, let's see,
A.
so this angle, so this angle has to be A,
Yeah.
so A over H over 2, okay? Does that make sense? Okay, so here's the problem. Let's say I have a 30-degree incline, and I'm trying to place a box up here, like so. Let's say the width of the box is 1 meter, and let's say this is uniform, you know, mass all through here. What's the maximum height? Is maximum height of box such that the box doesn't tip over. Well, actually, I probably should have divided you up in groups before that. Okay, so why don't we divide up in groups and do a few group problems? So just get about a group of 4 of the people around you, 3 or 4. And each group come over and go grab a whiteboard, okay?
Such that the box doesn't tip over?
Yeah, it doesn't tip over. All right. So I'll let you guys do that. When you're done, give me a number, okay?
Don't worry.
He didn't tell us we were trying to figure out the height. So it's gonna be
Oh, it's maximum height of the box, so
Yeah, so
actually,
it's gonna be-
meters, yeah.
yeah, so it's gonna be
So the maximum height of the box is just
1
times
meter.
2.
Yeah.
no.
That way I won't have to multiply by it.
Yeah, I got you.
So,
You could just put S.
yeah.
Oh, we got the eraser.
I know I assume it's natural. And
So you, there we go.
You get 1.7.
1.7
That's it?
Yep, that's what we got.
Thanks.
What is it? The weight. Don't worry about that.
Yeah, this is the angle with respect to
Okay.
the weight.
So that's all.
Yeah.
Maybe it's just a pilot.
That's the way that.
What?
Oh, I did like the island one. Ain't bad.
Oh, I thought this cost forever an hour and 8:40.
Like put down a ocean.
Oh, this is Tuesday and everything was good.
Okay, you ready to go through that? Okay, what did you get?
1.73 meters.
All right, how'd you do that?
We set it up tangent of 30 degrees equals.
The weight force goes down like this, right?
Yep.
This angle between a perpendicular and here is theta. I want this weight force, the line from the center of from this this point to here. I want it to go straight over the suspension point if I want it to be at a maximum. If I want it not to tip over. Here it would be tipping over, right? So I want to have the height to be such that this weight force would go right over the suspension point, or the rotation point. All right, so I need theta, tangent of theta, to be equal to h over equal to
1 meter
L
over
over 2, yeah, L over 2 over, well, half of a meter, right? Because I need that angle there, to be half of a meter, right?
But they cancel out when you.
Half of a meter over h over 2.
Oh, then yeah.
So that would be 1 meter over h. And so yeah, and then so h is 1 meter over tangent of 30 degrees. And what's tangent of 30 degrees?
2 squared.
Square root of 3?
Yeah.
Or 1 over square root of 3? All right. And so I get 1.7, right? Okay, let me give you another one real quick. This is more of a general work problem. I'm going to give you guys 2 minutes to do this one. So I have a wall. I have a tower that is leaning. Very narrow tower. Or very narrow. And then I have a rope. This angle of leaning from the vertical, we'll say, is 20 degrees. This isn't center of gravity, by the way. This is, we'll say that this is so narrow, it's just basically a rod, okay? Narrow rod. The length here is 2 meters. Center of gravity is right in the middle of this. And the mass is 100 kilograms. The height of the rope is 1.3 meters. And this is like a little hand down here, so it's not going to slip or anything. But this is the rotation point of the ground. All right, my question is, what is the tension in the rope? This one's a bit complicated. See if, as a group, you guys can get that. I'll give you about a minute head start, and then I'm going to try.
Where can you balance this work then?
Is the center of gravity or
Where that dot is, it's
So you said it's directly in the middle, right?
Yeah, directly in the middle.
Okay.
That's 1 meter.
Yep.
But it's at 20 degrees, so that's not quite how far it is from the ground.
This one's a little bit. I was going to say we needed to get that number. The ground or the center or whatever.
I'll give you a minute. You guys got 3 minutes to do it. That's not plenty of time.
Or free ball, you got her.
Yeah, let's do that.
of the weight force. So there's 20 degrees. So I guess it's actually. So that'll be the tension. And
I mean, that's
Does anyone? I don't want to write on this. It's kind of.
So like,
so that's opposite. So that's kind of 20.
but like,
Yeah.
So
And I need
I'm pretty sure we have to do this. I know that we have to do it. And then this tension is going to be multiplied by tension times 2 meters. Huh? And then for the... Oh, this is... Oh, you're talking about the tension. And then the other tension in the slot thing. So it would be... Oh, and there's G. There's G here too. Which one is negative?
I don't think so.
Which one makes it 1 to the 4? So clockwise.
I think this is
The tension is trying to clockwise. Yes, and then the other way. So this is negative.
Yeah, I would hang on my fridge. I have to hang on my fridge.
Because they're not going to the same point in objects. Like the same
So you just rememorize
yeah.
for this one. So this is equal to
Really? I think it's the 10. We have to divide it into components of y and x. Not I think it's for this one. I think it's going to be
Kristen kept going.
So what are we trying to find? Tension. What did you say? I have no idea.
I think you should be able to.
So you did the vacuum cover.
It's going to be, it should be
All right, boys. What do you got? I got it. 257.8. Did anyone get that?
No.
I have no idea.
All right. I'll tell you what. Time for you guys to go. We'll do this tomorrow. See if you can get that by tomorrow, okay? You're taking a 20 degrees
Yeah, all you have to do is take it.
Yeah, they got
They get extended. And they put
Alright, I gotta get the Thank you very much. 257.8, see if you get that.